start your presentation. So just a few words to say that I really would like to welcome you, Andrea, in this Open Be Healthy lab meeting at Concordia. Just a few words about Andrea and what he has done and what he is doing. So Andrea get a PhD thesis in 2003 at the University of Virginia, and followed by several postdoc at the National Taiwan University, at the Weizmann Institute of Science, at the University of Naples, and then moved to l'Université de Liège at the Cyclotron Research Center. So I think that when you move to Liège, we meet at that time and we start collaborating at that time. I think it's around 2010 or the things like that. So Andrea is now associate professor at the University of Western Ontario in Department of Physics and Astronomy, and principal investigator at the Western Institute of Neuroscience. His research program is around multimodal neuroimaging, so data acquisition, modeling, and application in normal subject, but also in clinical population. So his focus is mostly in methodological development in MRI, but also PET. And his lab focus on modeling the functional connectivity, which is like an area of research that we share between his lab and our lab. So this is a very important aspect of our connection, the research connection. So one of his lab recent research finding state that the brain is flat and claims the concept of dimensionality could bring important insight in the understanding of the way of information is transferred from one area to another area, and how we can also make this as a marker or biomarker to evaluate disorders, diseases, and disorders of the consciousness, for instance, which is one of his expertise in the neuroimaging data with application in consciousness. So today, his work is, or his talk is about advancing the Ising models to explore the role of metabolic alteration in neurodegenerative disease. And this is another aspect where his lab linked to our lab. So we have the same like focus on Alzheimer's disease. So thank you very much, Andrea, for having accepted our invitation, and the floor is yours.
Okay, thanks a lot, Raviv. It's always a pleasure to give presentation for your group, and I think it's I mean, it's an occasion, right, to just to share what we do with you, and to get as much feedback as possible, right? That's the best way to interact. So just stop me at any time you feel like you have a question or you have something that is not clear. So can you see the presentation?
Yes.
Okay, so so the idea of this presentation is mostly to show a possible strategy that we would like to use in neurodegeneration, and it's based on the Ising model, right? So as you already mentioned, the Ising model is a model that we have been using a lot in our lab. So there is no intention here to say that the Ising model is the model to use. Of course not. It's one of the possible solutions. And so what I would like to show in this presentation is that what is the advantage of the Ising model? And I will say right away that the advantage of the Ising model stands in its simplicity. Okay, so it's a simplicity and adaptability. Okay. So let me start by mentioning the relevance, right, of imaging in neurodegenerative disease. So we all know that the imaging has an important impact, right, in diagnosis, possibly in prognosis, in seeing where the disease will evolve, right, to see where the disease will evolve. And so, of course, one of the main and older imaging technique we know is PET, right? Stands positron emission tomography. This is an example of FDG PET that measure the metabolic glucose consumption or metabolic activity in the brain, right? So this comes just from a review from Rice and Bitzas. And so here we just want to show the effect of the Alzheimer on the brain. So you see an healthy control on the left, and you see a fully all brain metabolic activity, and then you see in the middle the effect of mild cognitive impairment. So you start seeing a reduction in metabolic activity, and then once the dementia is observed right at the behavioral level, meaning that the patient start suffering memory loss and other cognitive impairment, so you can really claim that the patient has Alzheimer, then you see a big depletion or reduction in metabolic activity. So we call it a hypometabolism, especially in the frontal area and temporal area, right? With the area instead of the visual occipital regions that are preserved, okay? And so this is telling us, yes, definitely, Alzheimer is a metabolic impaired disease, right? So in Alzheimer, we have metabolic activity impaired. And this is kind of counterintuitive with what Alzheimer comes with, right? This hyperexcitability that we observe, for example, with EEG or MEG, right? So we show an increased spontaneous activity, and that can come also with some epileptic event, right? And so, of course, this is why it makes Alzheimer's disease such a complicated disease to understand in terms of mechanism of the brain, right? Because how can it be possible that we have increased hyperexcitability and then we observe instead the reduction in metabolic activity? So this is just in the same review. This is just a summary of what it was the situation in 2017 for neurodegenerative disease like Alzheimer, frontotemporal lobe dementia with the Lewy body that it seems like to be the second source of dementia after Alzheimer's disease. And then also other sources of like vascular Parkinson disease. And so in this review, what is mentioned is that if there is an unclear consensus, right, for vascular and Parkinson's in terms of what are the effects of these diseases for metabolic activity, there is a more clear pattern in Alzheimer's disease with the temporal and parietal hypometabolism and predominantly hypometabolism in frontotemporal lobe dementia, and this is that specific primary visual cortex hypometabolism for the dementia with Lewy body. So this is telling us that at least when the disease is in its advanced stage, FDG PET can discriminate the different situation. So this is a study that was done by Cantarci et al., in which the idea was to see if metabolic alteration can be used, can be detected at the initial state, in the primary phase of the disease, and see if there is any difference, for example, between the dementia with Low's body and Alzheimer's disease. So here, what was studied was the patients were studied were patients with the mild cognitive impairment, right? That either developed in dementia with Low's body or in Alzheimer's disease, right? And so what you can see, so the comparison here is between control, healthy control, and mild cognitive impaired patient that develop in dementia with Low's body, so on the left, and instead on the right you have a healthy control versus mild cognitive impaired that developed in Alzheimer's disease. And so what you can see is that the pattern, right, the regions that show more metabolic activity in healthy controls with respect to MCI with DLB, it's mostly in the parietal, but also a lot in the occipital regions, right? And so we know that, in fact, the DLB is characterized by hypometabolism in visual occipital region. And instead, for the patient that have mild cognitive impairment but will develop later on in Alzheimer's disease, instead we do not observe this reduction in the occipital area, but we observe reduction in the temporal parietal region instead. Okay. For this study, it needs to be said that when they try to compare the two pathologies directly, instead of comparing them with healthy control, they were comparing directly, so DLB versus AD, they couldn't find any main difference when they were correcting for multiple comparison. And we know multiple comparison is relevant in neuroimaging when you do statistical analysis, right? So this is another study that was done instead using a different technique, which is an MRI technique. So MRI, we know that I always say that can be used like a Swiss knife, right? So it can be used to measure structural images. It can be used to measure fibers. It can be used to measure arterial speed leveling, to measure blood flow. Of course, fMRI to measure blood oxygen level dependent signals. So MRI can be used in many different ways. And one of the ways is diffusion tensor imaging with subsequent post-analysis, which is called tractography, that allows you to substantially to follow fibers, white matter fibers. And specifically in this analysis, they did tractography by giving specific region, target region and seed regions. So you fix a seed region and a target regions, and you're allowed to indicate, to extract the tracts, the fiber tracts that substantially unite the seed with the target regions. And here you can see three specific fasciculi, the uncinate fasciculi in yellow, the inferior orbitofrontal fasciculus in green, and the inferior longitudinal fasciculus in purple. And then what you can do, you can calculate the fractional anisotropy that we know measure substantially how water diffuse more specifically in one direction with respect to the others. And so you can measure FA along the voxel that are part of the fasciculus. And then you can check if fractional isotropy for each of the fasciculi is statistically different between one population and the others, okay? And so here we see in circle are the normal controls, the triangle are subject with the dementia with Lewy body, and the rhomboid are subjects with Alzheimer's disease, okay? And so for each, you have substantially three groups, right? For each of the three fasciculi, and respectively right and left, okay? And so what you see is that, for example, for the uncinate fasciculi, you have that for the right and left, both the subject with the Alzheimer's shows, so the subject with Alzheimer's shows reduced fractional isotrope with respect to control, and the dementia with Lewis body showed the reduced FA with respect to control for the right one, and then you see the rest. So this is telling you that, for example, we know that a reduction in fractional isotropy means substantially a reduction in the preference of water diffusion in one direction with respect to the other, which is an indication of fiber lesions, right? So every time that we observe a reduction in FA, we can attribute this to, for example, a demyelination of the fibers or so on. So again, this is telling us that by just looking at the specific imaging technique, we can characterize different sort of dementia. What about resting state fMRI? So we know the seminal work by Gracious et al. So this is a very long time ago. It looks long time ago, right? 2004. And so this was the first study, from what I remember, on Alzheimer's disease. So he started using independent component analysis. So at that time, mostly was seed-based approach was the one that was used. So he used independent component analysis. He extracted one of the main network, which is the default mode network. And so he realized that when you compare the Alzheimer's disease patient with elderly, so age match subjects, so there was a significant reduction in regions like the precuneus or the hippocampus or the entorhinal cortex, which were part of the network. And then he defined this goodness of fit, which substantially is telling you how much the network, and specifically in this case, the default mode network, fit to specific templates of what should be the spatial pattern in normal subject. And he showed that the goodness of fit in Alzheimer's disease patients was much lower than in elderly, showing that substantially the spatial pattern of the default mode network was affected by the disease. Now, since then, of course, there have been many different applications of resting state fMRI, but it needs to be said that still resting state fMRI, at least in Alzheimer's disease, doesn't look like it's still controversial, right? So meaning that by itself, it cannot be so conclusive in terms of diagnosing. And as usual, the main point is not just to have a diagnosis of the pathology when already the disease is so evident in its behavioral aspects, but to be able to predict the evolution of the pathology when you are in the mild cognitive impairment phase. So, of course, so far, I just showed what people can do by using separately imaging technique. And that's something that I think it's always very much important, right? So that's the very first step that you want to do. You have an imaging technique, you extract images, and then what you want to do is to compare the images in a different population and do the classical statistical, sorry. The classical statistical comparison between control and a pathological situation or two different pathological situations and so on. So I think it's a must when you acquire images. Then, of course, something more than can be done is to try to combine different images, okay? And one way to combine different images is by using modeling. So this is a study that came out very recently by Pato et al. In 2023. And so what they want to do, they want to use substantially a mean field neuron mass model, right, that was developed previously by Deco et al. And so what they want to do, they want to predict functional MRI using structural connectivity. But in this case, not only they use structural connectivity and the neural mass model on top of it in order to predict the both signal and then functional connectivity. But they want to use substantially information from other imaging technique like PET, and specifically they use the amyloid beta PET results and the tau PET results as input for their model. Okay, and so then what they do, they use an excitatory inhibitory model, right? Balanced excitatory inhibitory model that was developed for healthy control to predict fMRI. And what they do, so each of these BEI predicts the activity in each of the node. So they have their own parcellation scheme, and each of the patch of cortex is modeled by this BEI, so this balanced excitatory inhibitory model. And then they use the structural connectome to couple the activity of the different parcels. Okay. But so on top of that, because they're trying to model Alzheimer's disease, then they use the amyloid beta PET and the tau PET as input to modulate the balanced excitatory inhibitory model. Okay, so so the idea is that they use the scalar map locally. So for each of the patch of cortex, you have, of course, a value for the scalar map for both the amyloid beta and the tau PET. And so for each patch of cortex, there will be then a different modulation of this EAI model. Okay. And then what they do, they simulate the brain activity, so the bold signal in each patch of cortex, and then they calculate a functional connectivity matrix. And so here, what you see specifically, you see like what is called a time. So what is this? So that's so what they do here. So once you have the bold signal for each region, you calculate the Hilbert transform, and then the Hilbert transform give you an amplitude as a function of time and a phase as a function of time. And so what they do then, they look at, so of course you get a phase for each of the region, and then you can calculate the cosine, given two region, you can calculate the cosine of theta I minus theta j, okay? And then once you have that quantity, what you can build substantially, and for each time, you can build an n by n matrix. So if you have, let's say, t time, you substantially build n by n correlation matrix in this way. And then what you do, why this is a time by time, so substantially you look at how the correlation matrix built at time t1 will correlate with the correlation at times t2, 3t, and all the other time. Okay, so you see in the simulated phase functional connectivity dynamics matrix, the diagonal, of course, it's all one, because a correlation at time t, the functional connectivity at time t correlates with this itself at the same time. And then when you move away from the diagonal, you see less and less correlation. Okay, so this is just the way to measure dynamical functional connectivity. And then, of course, you have the simulated functional connectivity, and then you have the empirical, and then the idea again is to fit your parameters in such a way that you minimize the distance. Okay, now what are the results? So here, okay, so on the left you see an optimization of G. G is the global coupling that substantially is used to fit the structural connectivity main coupling. So there is a global coupling from the structural connectome that is optimized at the global level, right? And then you see two examples of the functional dynamics. So this is region by region, right? So this is for a specific time. And you have the empirical, you have the simulated. So on the bottom, you have the 6 scalar map, average scalar map that you have for amyloid beta and tau PET, so of course for healthy controls, and then for MCI, mild cognitive impairment, and for Alzheimer's disease. Okay, and so then what they found is the following. So here, if you look at the last column, well, you have substantially the Kolmogorov-Smirnov distance, so this measure. So of course you want the distance to be as small as possible, because if the distance between the empirical and simulated is small, means that your fit is very good. So what do you see here? You see that when you look at you put in the model both the amyloid beta and the tau PET input, you get the best fit. Okay, and then when you look at just the amyloid beta and the tau, okay, you see that the fit is a little bit worse, right? It's worse. And then the BEI means that you're just using the balanced excitatory inhibitory model, just without introducing the information from the PET, right? For the amyloid PET and the tau PET, okay? And so now in the upper panel, you have the fitting for healthy control. In the middle panel, you have the fitting for mild cognitive impairment. And in the bottom panel, you have the fitting for the Alzheimer's disease. So when already the disease is strongly appeared. So what do you see here? You see that even for healthy control, to use the information from the PET, amyloid beta PET and tau PET, help improve the model. Okay, because you see, BEI is the model that was initially built for healthy control, right? And doesn't have the input of the two PET. And then you see that even for control, you have that the distance is smaller when you consider both amyloid beta and tau PET. Then what about the situation for MCI? For MCI, again, the fit is the best. But you see that, that's an important thing, that for mild cognitive impairment, as well as for the healthy subject, the distance between when you use just the amyloid beta or when you use both is not that big. Meaning that it's mostly the amyloid beta PET that helps improving the fit and not the tau PET. Because you see, when I just use the tau PET in both healthy controlled and mild cognitive impairment, the distance gets much bigger. Meaning that the tau PET, it doesn't help the fitting for in control, and also doesn't help the fitting by itself in mild cognitive impairment. Meaning that when we are in the primordial phase, it's mostly the amyloid beta that helps to understand what is happening, the mechanism there. Then instead, you see, when you look at the lower panel, then the situation is inversed. So when the patient really suffer the consequence of Alzheimer's disease, so all the manifestation of Alzheimer's disease is present, then the amyloid beta PET doesn't help anymore. It's mostly the tau PET that helps to explain the Bolt signal. And you see that the distance between when you use only tau PET in green, and when you use both amyloid beta and tau PET, is substantially the same. So this message is very strong. So by using a modeling on top of the imaging, it's telling us substantially something about the mechanism and the relevance of the two components, right? So amyloid PET, so the amyloid increase in the mild cognitive impairment may be more relevant than the tau PET for the first phase. And then when the disease is appearing in all manifestation, then it's the tau PET that can explain most the Bolt signal. So now, let me show what we can do with the resting Ising model and why it's still working. So, of course, a neural mass model has been very evolved. So I didn't mention, for example, the previous work to this one by Stefanowski that appeared on Frontiers, and they only look at they only look at the effect, the PET amyloid beta PET, so they didn't introduce both the two input. And so they also were able, using the virtual brain, right? You have been exposed to the virtual brain during the school that Habib organized. And so, so they use the virtual brain and they use the amyloid beta input in the virtual brain to explain, in that case, the EEG activity and local field potential. And again, they show that when you introduce as input the amyloid beta, you get a better fit of the spontaneous activity. And you can show this hyperexcitability that we were talking about. So here we have this very important model that have been developed that explain the mechanism and give you an understanding of what's happened. So the point is that why do you need to use a model from physics that explain ferromagnetism to just explain the mechanism of the brain when you have already something that looks very much complete and very much promising? So the idea is always the same, that physicists by nature tends to simplify things, okay? And simplification is not always good, it's not always the way, but by keeping things simple, it makes you feel like you have a better grasp of things, and simplicity also permits adaptability of the model, right? In a way that is not so clear when the model is very complicated, like a neural mass model. So let me introduce what is this Ising model. So the Ising model, substantially, very quickly, it's a model that explains ferromagnetism. So ferromagnetism are made of, so you have magnets, you have magnetization, right? And so usually in the ferromagnets, you have domain of spins, right? And the spins tend to align to each other. And the ferromagnets is embedded in environment at a certain temperature. And so what the Ising model was mostly study is to study phase transition in ferromagnetism, how a system can be explicit, show ferromagnetic properties. And so and the main important things is that we know that temperature plays an important role in physics. And so substantially, what has been shown is that there is a phase transition when you go from low temperature to higher temperature. And what is happening is that at the lower temperature, the spins tends to be aligned. And when you increase the temperature, instead, the spin tends to be oriented in all possible direction. And so you go from an order phase to a disorder phase, and the properties of the material change completely. Now here, what we want to do with this model. So substantially, we want to simulate the Bolt signal. And again, when we want to simulate the Bolt signal, we claim that we model what we measure. And of course, after doing some preprocessing of the Bolt signal itself, okay? So the idea is that the spin want to represent the activity of the Bolt signal, either active or disactive, right? And each spin is associated to a specific region, and we will see later on how substantially it works. So just to say quickly what the Ising model does. So this is an Ising model in 2 dimensions. So for each lattice size, the spin can be either up and down, right? And the spin, the energy of the Ising model is just given by a common coupling, and then sum over Si and Sj. So because there is a negative sign in front, the spin wants to be oriented always at the same time, in the same direction. And then there is the possibility to have an external magnetic field So the spin, of course, again, wants to be oriented in the direction of the magnetic field, okay? And so here in this specific model, so this is a 2D Ising model. And so usually you have that the spin is coupled with only the nearest neighbor, right? The fourth nearest neighbor. And what is the main things? The main things is that, and what I will show later on, is that substantially an Ising model, why it's so important? Because even if there is a local interaction, so meaning that the spin can feel only the spin that are in its nearest neighbor, then at the critical temperature, this model can show substantially global behavior. And when you show, meaning that you show global behavior, means that the correlations decay in a power law instead of having an exponential decay. So what are the properties that you measure for an Ising model? So it's energy. And so the energy tends to increase with the temperature. Then you have magnetization. And the magnetization is telling you substantially is the average direction of the spin. So if all the spins are aligned, the magnetization is high. If the spins tends to be aligned in different direction, then the magnetization becomes low. And so as you can see, there is this temperature at which you have a very sharp transition from the phase in which the spin tends to be very much aligned to the phase in which the spin tends to be disordered. And so this, we call this temperature critical temperature, and that's the temperature at which, for example, the susceptibility increase, and the susceptibility is nothing else than how susceptible is the system when you change the temperature. And so at the critical temperature, you have the highest susceptibility because a small change in temperature makes the system change abruptly, okay? Now, what is the beauty of the Ising model? So the beauty of the Ising model, as I was saying, is mostly in the fact that it's a model that can explain emergent property of collective behavior. And what do we mean by that? We mean the fact that even if the coupling, it's only local, meaning that the spin, it's only coupled to the nearest neighbor. Well, what it happened at the critical temperature, this temperature here, the correlation length go to infinity. So if the lattice size is an infinite lattice size, the correlation length goes to infinity. It will be finite if the lattice, of course, it's just finite. But so at this TC, because the correlation length becomes very high, you see that the exponent of minus r over xc that control the correlation between any two spins. So you take any two spin and you see how the spin correlate by generating many configuration. You check how the spin go with themselves, right? So if by generating many configuration, you have that the spins tends to be either up or down, then it means that they correlate. And so then usually you expect only spin that are very close to correlate, right? Because they are coupled. So how come spin that are so far away in the lattice can still correlate? And it's happening at the critical temperature, because at that temperature, you have that the correlation length becomes very big, meaning that the decay, this exponential decay is substantially 1. And so the correlation decays only as a power law of the distance. And the effect is that you see at the critical temperature, you have the formation of these blobs, meaning this domain of correlation that are characteristic of the Ising model, okay? So at the very low temperature, the system is frozen. At very high temperature, the system is very chaotic. And the criticality, you have this formation of domain. So now, how can you simulate dynamics, right? So then what you can do, you can now simulate dynamics. Even if the Ising model is completely not a dynamical model, you can still simulate dynamics, okay? Meaning you can generate different configuration that correspond to different time point. And the way you do it, substantially, you create a configuration of spin, and then you test the spin for flip. And there is this Metropolis algorithm that substantially, so if the energy when you flip is minimized, you accept the flip. If if the energy is not minimized, well, you still accept the flip in the case that the energy is, in the case that a random number that you extract will be smaller of the Boltzmann factor. And the Boltzmann factor depends on the temperature itself. So it's E up to minus delta E, the change in energy over K Boltzmann T. Okay, so then this means that in this model, you can also accept changes in flip if the temperature is sufficiently big. Okay, and so then what we do, you substantially, you generate as many configuration as time points that you want. And then, of course, substantially, you have a sequence of 1 and -1, which represents your time courses. And then once you have the bold signal generated, you can calculate your correlation matrix, right? Substantially, you simulate the bold signal, and you can build the simulated functional connectivity. And so as again, you start with the random configuration, then you make the system thermalize, and then you generate as many time course, as many configuration as the time points you want to simulate. So this is the characteristic time configuration of one lattice size, and then you have as many lattice sizes as the parcellation scheme that you have, and you build your correlation matrix. And so this is what we do in the generalized Ising model, in which substantially we use now as input for the coupling the structural connecton, right? So each region of the lattice correspond to a specific parcel in the brain, and different regions have coupled according to the structural connecton. Okay, so the structural connecton becomes the input of the Ising model. And of course, if two regions are highly structurally connected, then they are more coupled, and so they will tend to correlate more. So when they flip, they tend to flip together. And so here are the property of the generalizing model versus the 2D Ising model. So the 2D Ising model is the classical square lattice size, and the generalizing model is the model in which the coupling now are induced by the structural connector. And then here you see what is happening. So of course, the 2D classical Ising model is a model in which region of the lattice size do not match with the region of the brain. So when you calculate the functional connectivity, of course, it doesn't make any sense, right? Because there is no match. But now when you calculate the functional connectivity in the generalizing model, you have a match between the lattice size position and the empirical region of the brain. And so then you expect, if your model does a good job, that your correlation functional connectivity matrix will match over the one with the empirical one. Okay, and so this T-min is the functional connectivity at the best fit, and this will be instead the functional connectivity at the critical temperature, which is the temperature that is completely determined by the model itself. Okay, so now why the Ising model can be important? Well, because one of the properties of the Ising model is the flipping frequency. Okay, and so now let me just mention very quickly the study that was done by Guldemann et al. And so what we studied with just resting state fMRI, we extracted using ICA the different network that you observed. And here you see on the 4 column the different network in 4 conditions: wakefulness, mild sedation, and responsiveness. So when propofol was fully working, and then recovery after the effects of the anesthetic were washed out. Okay, and so what you see here is this fingerprint. So this fingerprint that has a bird type shape, and so these are properties both temporal and spatial of the component. And then what you want is that this fingerprint has this bird-shaped type, because we'll confirm substantially that you are catching a neuronal network. And when we need neuronal network, let's say, for example, we have that this quantity needs to be maximum, and this is the frequency of the Bolt signal, that in this case was between 0.02 and 0.05 hertz, okay? Now, what is happening? It's when you look for neuronality, so when you look for the network that have been show a pattern that looks like the pattern that you're looking for, but then you look at these neuronality properties, well, only a part of the network show neuronality. And so here you see that, for example, for the DMN, 100% of the subject show this neuronality property when they were awake, but then in the condition of propofol, only 60% of the subject show this neuronality condition, meaning that the Bolt signal is kind of changing in nature, okay? So it's not showing the frequency pattern that it shows when you are awake, okay? And so here, what do we see? We see that when you look at the regions that show substantially a bigger disconnection in functional connectivity, and you can see it also here by looking just at DMN, right? You see that substantially the medial prefrontal cortex is completely gone from the network, is disconnected, right? And so what is happening? Well, what is happening is that if you calculate just the mean frequency of the Bolt signal, well, these frontal regions are the regions that show an increase in frequency. So the regions that tends to be disconnected in the DMN are the regions that show an increase in frequency of the Bolt signal. So what is this coming from? Okay, and so then the point is that what it could be is that the Bolt signal, so the Bolt signal frequency is related to the metabolic activity of a specific region, okay? And so now this is an example of metabolic activity in patients that suffer a severe brain injury. So this patient went to coma, and then after a few weeks exit coma and went in a state is called minimally conscious state. So it was completely just mildly unresponsive. And so you see that the metabolic activity on the left hemisphere is completely gone. So it's completely hypo, and the metabolic activity is preserved only on the right hemisphere. Now, if you look at the Bolt signal, you have that the Bolt signal tends to have a low frequency in the regions that have high metabolic activity, and tends to increase in the regions that have low metabolic activity. Now, when you have results like this, you can interpret in two ways. One thing you could say, oh, because there is no more neuronal activity in the left hemisphere, what substantially I'm capturing is the high frequency signal of the Bolt that we know already related to vascular phenomena, right? That's the reason why in the fMRI community, we bandpass filter the Bolt signal to remove, for example, the high frequency that we claim to be vascular related, right? Or the very low frequency that may be, for example, the warming up of the scanner. So then you may just say, okay, because substantially there is no more neuronal activity here, what we are capturing, it will be just some artifactual nature component of the Bolt signal that was not completely cleared away. But on the other end, what we could have is that, in fact, the Bolt signal is still neuronal, but is changing in nature, meaning that it's changing in frequency. And that's something that in the EEG community, everybody knows. Everybody knows that when you fall asleep or when you're anesthetized, there is a change in power, a transfer in power from high frequency, beta and gamma, to the lower frequency. So everybody knows that this is a clear pattern, right? But why in the fMRI community, we keep saying instead that the neuronal activity needs to be in the specific range of frequency and that's it? We could also observe a transfer of power from low to high when something changed so drastically, like, for example, falling asleep or being anesthetized or suffering a pathological condition. So my claim is that the Ising, the Bolt signal can change in nature, and that there is a shift in frequency every time that metabolic activity is reduced, and specifically that every time that metabolic activity goes down, there is an increase in the frequency of the Bolt signal. But now you go back to the Ising model and you say, can the Ising model explain that? Well, the point is that even if the Ising model is such a simple model, in fact, it can explain this, because you can see here, this is the simulation of the spin flip frequency for the gym, right, with the temperature. And you see that when the temperature increases, substantially the spin wants to flip at higher frequency. It just makes sense. And so then it means that increasing temperature can increase the frequency of flip. But now, how can we explain the fact that in different regions of the brain that the frequency will be different? Well, we need to introduce what we call the concept of local temperature, which is just the global temperature that now will be the only fitting parameter, multiplied by the FDG PET at a certain power alpha. Okay, and so this will make substantially, by introducing the concept of global temperature, of local temperature, we give the possibility of different regions of the brain to flip a different frequency, and so to explain the change in frequency of the Bolt signal in different regions. And so this is an example not done with the Bolt signal, no, sorry, not done with the FDG PET, but using just the graph strength. Okay, so here for this model, we look at the Ising model for each of the networks. So each network was represented by an Ising model. So each network is 5 regions. And so we simulated as many Ising models as the network. And so we introduced the concept of local temperature. So we have 5 regions. So we have 5 local temperature, which is the global temperature, which is our fitting parameter, times mu I. As mu I, we just took the graph strength of that region. So how many connection in terms of structural connection that region has with the rest of the other regions. And alpha is the other fitting parameter. So now we have 2 fitting parameters for the Ising model, the global temperature and alpha, that will tell us with which power this parameter mu I is entering. And so you can see that substantially, you see, for example, for auditory, you have that the graph strengths of different regions changes, and alpha in this case is positive. For the singular opercular, we have that alpha is negative, so we substantially, we have that bigger graph strengths will imply smaller local temperature and so on. Okay, so different network, because they have different structural connectivity, then will be will give different alpha. And then here the most important thing is that, okay, but what is happening in terms of fitting? So here you have just J premodel, meaning if I take that's just a structural connectome, and I see how the structural connectome is distant from the empirical functional connectivity. And so this is the distance, right? The distance from the structural connectome and empirical functional connectivity. On random J, this column, I have the distance from simulating the Ising model with just the random Jij. So I take a random Jij, I simulate the Ising model, and then I see how the functional connectivity match the empirical functional connectivity. And the post model means that I really take the structural connectivity as measured by DTI and then tractography, and then I simulate the Ising model. Okay, and so you see that all the time the model does better than just the structure itself. For the other, for example, random does equally well than the post model, meaning that substantially the model is not really useful. But then you can see that, for example, for the single parietal, the default mode, the dorsal attention network, the frontal parietal, right? The model always does much better, not only than just the structural connectome itself, but also of a random JIJ. Okay, and so this is telling us substantially that by inputting a structural connectome in the model, we get a better fit of the functional connectivity than just using the structural connectome itself. And so this is for the different networks, for just the sensory network and the higher order networks. Okay, just to see how things go. And then, for example, let's look at the retrosplenial. You see that this is the structural connectome. This will be the simulated empirical, the simulated connectivity for a random JJ, and then this is the simulated from the empirical JJ, and this is the empirical functional connectivity. Okay, so for example, for the retrosplenial, you see how good the model works. Okay, and you see that this is what is happening for the reduction in the distance. Okay, so now what is happening here? So what we can do? Well, how can we then implement this model for example, for neurodegenerative disease? Well, the idea is that now, substantially, what we can do is that we can substantially introduce the concept of local temperature, and so then use now for the Ising model, not only as input the JJ that comes from the structural connectome, but then introduce the scalar map to modify the local temperature, to define the local temperature. And so, for example, I can define a local temperature as the global temperature that will be my fitting parameter, times the FDG PET. For example, I can put the FDG PET, the metabolic activity, exponentiated to an alpha. I can put the tau PET exponentiated to a beta. I can multiply by the amyloid beta PET exponentiated to a new exponent. And so now substantially I will use the global temperature and then this exponent as my fitting parameter to get the best fit. Okay, now what is the signature in this case? The signature is that different region will have now different Ball frequency because they experience different local temperature, and local temperature means different frequency for the Ball signal, meaning that we will have a way to check if our model can really predict the change in frequency in the different region of the brain. So you will have a fingerprint, a signature. What you can also do? Well, in fact, we saw that there are two ways to modify the Ising model. One is to introduce this concept of local temperature. The other way is that let's keep the temperature global, so there is no local temperature, but now I introduce a concept of external magnetic field. And my external magnetic field can be a profile that is the profile of the scalar map. Okay, so substantially, I have that my external magnetic field will not be homogeneous in space, but will be higher if, for example, the metabolic activity is higher, and will be lower if the metabolic activity is lower. And then the external magnetic field that show the spatial profile of the metabolic activity, it's coupled to the spin. So spin that have higher, so spin, if the metabolic activity is higher, then the spin want to align in that region and so on. And we can use as many magnetic field as the scalar map that we have. Okay. And so then now the fitting parameter will be global temperature again. And then there will be alpha and beta, which substantially is telling you how much strong you want this scalar map, each scalar map to be relevant. And again, we will have different region, we'll have different Ball frequency, because substantially, if a external magnetic field is higher, then it wants to be the spin aligned. And so the effect of the temperature on the spin flipping will be less efficient. So now, can I just take 5 more minutes? No, Habib, I cannot hear you.
Yeah, sorry. Yeah, I said that the room is used in 5 minutes. So just
okay, let me just finish
yeah,
with the strategy.
Yeah, please.
Now, because we have substantially two parameters, which is the critical temperature. So the critical temperature is a property of the model, meaning that it's not a fitting parameter. Once both the Jij are inserted as coupling and the scalar map are inserted as is either affecting the local temperature or the external magnetic field, Tc is a property of the model. It's not a fitting model. And the same things, the dimensionality is a property of the model. So the dimensionality of the Ising model, right, that substantially controls how the correlation decay with distance, is also a property of the model. It doesn't depend from the fit. So this is my last slide. So this is the strategy that substantially we propose. So use structural connectivity and scalar maps like FDG PET or tau PET or amyloid PET as input for the gym. Then you use them as input, and then you put them in the gym, and then get the best fit for predicting resting state fMRI functional connectivity. Okay? Then confirm that your best fit is better than random prediction, meaning you start, for example, taking a random Jij or a random tau PET, a random amyloid PET, and then make the prediction and make sure that the prediction that you obtain by using the real input is better than the random one. So this means that your fit is good. Then extract the critical temperature and the dimensionality of the gym, that, as we said, they are not quantity of the fit, but they're just quantity that depend on the Jij and the scalar map that you're inputting. And then use this Tc and D for the classification or the diagnosing of the patients. Okay, so then it means that there are two properties that are not fitting parameter, but depends only on your input, meaning your structural connector and your FDG PET or other PET maps, and then use this parameter for the classification. Okay, because these are very strong, because they do not depend on the fit. They only depend on the initial input. And why this is important? Because when we do fitting, especially if the space is very high dimensional, we know that there are different parameters. You can have different solutions. You can play with one parameter and then another, right? There are different solutions that give you the same best fit. But here we are not using the best fit parameter for classification, but instead we are using the parameter that depends only on the input, right? And they're fixed. Once the input is given, once Jij is given, once FDG PET is given, there is only one single Tc and one single dimensionality. And these are the parameters that now can we use for classification. And why we can use them? Because before we check that the fitting of the model was anyway good, meaning that our model makes sense. Okay, so this is people that do the job, and thanks a lot, and sorry for being a little bit long.
No, not a problem at all. Thank you very much, Andrea, for this very interesting talk.